So hello again, everyone. This is a talk about Mobius, writing my own .NET runtime running on .NET Core. I've said previously a few words about myself, so I will just skip it now for now because I don't uh, feel it is worth to mention again everything which is about me. Let's go straight to the topic. First of all, have you ever wondered how .NET Runtime works? And this is probably, I hope you did, but maybe you didn't find a good motivation to find it out. So you are very interested, but in general, it seems to be very complex topic. So let's ignore it, right? And maybe on the other hand, maybe have you ever another question? Have you ever dreamed of contributing to .NET Runtime? And again, probably you was, even if you do, so you was afraid of doing so because it is so huge and complex thing to do to contribute to huge .NET runtime. So this talk is a little bit of answer to those two questions and about this Mobius thing. If you have watched my conference talk from the previous year on update, it was more practical. Let's say it was about high performance patterns in C#, so you could straight take some things from this talk and move it to your everyday job. This year, my talk is pretty on the other side. It is not super practical. It is super fun, and it is to inspire you, maybe to learn, to teach you something. But you should not expect that you will be able to gain a knowledge that will be super useful from the tomorrow. But still, I invite you to stay and listen because I found this topic interesting. So Mobius, after all those introductions. What is .NET in general when we are considering writing our .NET runtime? So .NET in general is a specification. We would like to see it as a language or maybe libraries or maybe some other stuff. I frequently calling it an ecosystem, but it is just a specification that was provided by Microsoft. It is standardized in ISO or and ECMA documents, which simply specify what should and how we should execute code at some runtime environment, which will allows us to run high-level languages. This is a strict definition of the .NET in general. And this specification, which is specifying .NET, is called Common Language Infrastructure. So this is defined in, for example, ECMA 335, Common Intermediate Language. This is the general name for this standard about common language infrastructure. And there is anything that is needed if you would like to write something which is .NET compliant, for example, .NET Runtime. Do not confuse it with another ECMA, which is just the specification of the C# language. This is strict about the .NET itself. By the way, if you are interested in .NET, I invite you to skim through this document. You can find interesting stuff there. For example, answer to the question, how many arguments can be in a method? Very practical knowledge, but some nice things to find out. They are all defined in this document. And to start to read about it, there is a great blog post from Matt Warren taking a look at this standard. So you can start from this document, from this blog post to start reading it. Okay, so we have this common language infrastructure, which is just a definition of all this thing. And what's inside this standard, let's say. So this is it has four elements. There is a common type system, which is just the definition of a set of data types that should be available when you are writing CLS compliant thing, CLI in fact. The metadata that describes the program structure and the data that should be exposed and provided. The common language specification is a set of rules to define for languages that want to run on this in this ecosystem and want to have CLS compliancy. We will return to that in a moment. And then the most important part for us is a virtual execution system. So it is the description of the runtime in the end, the part that loads and executes the CLI compliant programs using the metadata. This specified also that we are, and then we are able to run our program. So it simply is about CLI compatible programs should also compile to something that is called Common Intermediate Language. Probably you have heard at least once about intermediate language. Those are all those pieces that are specified in this ECMA. So one side note about common type system and common languages specifications, because I said that there is this common language specification that specifies languages that are CLS compliant, which means they should run on this .NET thing. And it is interesting thing to find out that common language specification is just a subset of a common type system in general. So you can create a language that will run on .NET runtime, for example, but will be not CLS compliant. You can, one example, unsigned integer is not CLS compliant. So if you are using unsigned integers in your application, this is not a CLS compliant code. Another thing is that public, just one example, a public field which starts with underscore is also not CLS compliant. So if you create a C# application with this type of field, it generally will compile unless you will provide this attribute that you want to generate a CLS compliant code. And on this, from now, it will not compile because it will complain that this particular field is not CLS compliant. So it is interesting finding, like in just one sentence, that C# is not CLS compliant by default. And that's okay. Like most of the times we are using languages like C# and libraries written in C#, so no one cares about interop between different languages because it's mostly C# in the end. Okay, but that was only the side note. What about the runtime then, which is called virtual execution system? So it is just a piece of code that is able to execute the CLI code, intermediate language code, which obviously knows about common type system and metadata. And in fact, it ignores compliancy into the language subsystems, language system. So this runtime is a piece of code. We have few, in fact, runtimes currently available. Obviously, we have .NET Framework, we have .NET Core, which is now called altogether as .NET 5. We have Mono. We had the .NET Compact Framework and .NET Micro frameworks, pretty not so popular edge case runtimes for small devices. There was open source Rotor, we created for academical purposes, and some more even experimental, like for example .NET Anywhere, created by a single guy from Google, Chris Bacon, that in the end turned out to be used as a very initial prototype for Blazor, and .NET GNU, some Linux based outside of Microsoft approach to create the other runtime. Okay, what is common for all those runtimes is that they all happen to be written in C, C++, obviously, because it is low-level programming language, the obvious choice for something that you write something fast and it operates on the unmanaged resources and so on and so on. Maybe in future we will see the runtime written in Rust. Sebastian has given today a talk about the Rust language, which is really powerful language for such purposes. So we can expect .NET runtime being written in Rust in a few years, months. We will see, but it all may happen. What's interesting for us that not every piece of the .NET runtime is written in C++. So there are pieces of the .NET runtime which are not strictly written in C++. The case is, for example, in .NET Core itself, where more and more parts are being ported to C Sharp, uh, which may happen, and you can find it pretty strange that we are porting something from super fast unmanaged C++ code to C Sharp code. But it has some benefits like better maintainability, obviously. Um, let's say community may be even more willing to contribute to something that is written in C Sharp. But there are also better performance advantages, like for example, there will be better interoperability between the code because GC will better work with the managed code instead of calling unmanaged code, one of the examples. So, not digging into that, there are some parts of the .NET Core runtime that are ported to C Sharp. Even JIT, some parts of the JIT and GCs are ported to managed code. Threadpool will be, and there is a plan to rewrite Threadpool from C++ because currently Threadpool is mostly based on the runtime code, and there is a plan to move it to C Sharp to the libraries. Compared to of enums, where recently .NET 5 moved from C++ to C Sharp, and it turns out to be twice as fast as the previous version. So it seems that it is a pretty good direction because of some advantages that parts of the runtime are managed. On the other hand, there were runtimes that wanted to benefit at what is most possible way in a most possible way of using managed code. So there were approaches to write the runtime which is mostly written in C sharp, for example. So Core RT is an example of that, when many parts were rewritten totally from C++ to C sharp, like type system and anything else. But still, in such a runtime, some parts are still written in C++, the most crucial parts like GC or JIT. So, most of the runtimes are written in C++. I said part of them sometimes are written in C sharp, but what if the managed runtime itself is managed totally? And so there is literally no C++ code inside, and whether has anyone tried? So there are two projects related to that. First of all, there is in JVM world something which is called Graal VM, which is similar approach to Core RT when most of the code is written in Java, but JIT and some parts are still written. JIT is written in Java, but still some parts are written in a managed code, but they succeeded in something that Core RT was trying to do. And there is also Yikes RVM, I'm spelling it that way, I'm not sure if it's correct, which is JVM virtual machine written in Java. And it requires only very small C-based bootstrapping, but in general, the whole runtime is Java-based. And this is exactly the thing that I was trying to reproduce creating Mobius. And Yikes RVM is just the Java runtime written in Java. So it seems that my idea to write Mobius was not totally idiotic because someone did it in case of JVM. So obviously I started to find out what are the purposes of JXRVM. And the name is Research Virtual Machine, and it explains it pretty well. So the goal of it is to provide flexible, open, experimental test bed for prototypes of virtual machines and some technologies inside. So it drives the experimentation and experiments simply because it is written in Java. It is much easier to experiment in high-level language than in C or C++. And it turns out to be a pretty good and it was a success because, as the Yikes states, it was a useful vehicle for research, as they are stating. almost 200 publications about the technologies related to the Gixer VM and so on and so on. So it turns out to be pretty nice idea. So in general, why writing managed runtime in managed code? First of all, if we would like to search any real world, let's say even economical or adult reason, let's say it like that, it would be research and experiments. So it is much easier and faster to prototype parts of the runtime in managed high level language than in the low level languages. Obviously, personally, writing something like that is a huge and super nice source of learning. So we need to learn about the structure of the runtime, how the runtime itself is working, what are the contracts that the runtime should meet, and so on and so on. So learning purpose is a huge point for me personally. Also abusing, let's say, or maybe in softer words, learning C sharp and the new things that are coming, because it is all a huge experiment. So when .NET 5 adds something, I immediately find two ways and points when I can add those points to Mobius, because it is so experimental. I'm trying to use the most experimental C sharp features available, so I probably will soon move to C sharp 10, at least as fast as it will be available. And also fun because I like the stuff and like digging in. So writing something for fun without any outcomes expected is really nice pet project. And one very controversial point, whether it is performant or not totally, probably it will be much less performant, not because of the heart of the things, how the first things are working inside, but because of the fact that I'm alone. So I'm not able to write something so sophisticated as the Microsoft having billions of dollars and tens and hundreds of developers involved in .NET. So just because of that, it will be for sure much slower. So meet Mobius. The idea has been coined. The experiments, learning, fun, and that's all. If you find it interesting, I will invite you to contribute, obviously. So I said, why now how? How it is working. We have a Mobius as an idea of the .NET runtime, which is running on .NET Core, which is obviously also .NET runtime. So it seems pretty crazy and stupid, in fact. And we have those three blocks in this picture, overall picture of these pieces working together. Our .NET application is just something that someone has written, so it is out of the scope, obviously. We need to run it. And instead of running it directly on the .NET Core, I'm running it of the another .NET application, which is Mobius, that happens to be .NET Runtime. So it will be able to interpret and execute the code from my app as it was a runtime. And this is written in C sharp using .NET Core, obviously. So it is just a middle block in between. And this sounds pretty crazy, right? So what Mobius is doing is, and in the end, all this makes a little bit of sense, is that Mobius as a runtime is still using JIT, so the just-in-time compilation that takes the IL of your application and still emits a native code of it. So it is just a proxy, but in the end, your application still is running as a native application, you executing binary code. So from the perspective of the application, it doesn't matter so much whether this native code has been emitted by .NET Core or maybe by my own runtime, because it is still just a code to execute. So we have this picture as a summary. We have the application that we want to run that was provided to us, and it has the IL, obviously. So the main work is that Mobius JIT is generating the native code of this IL code, and now we were able to execute this application at the speed of the native application because it is just native code, like the every JIT is doing. Obviously, this is a managed environment, so sometimes the JITed code produced by Mobius will call some code from Mobius to get some features from the runtime. For example, the JITed code will ask the runtime to allocate an object. So we will have from time to time some calls from the native code to our Mobius code, and then the whole machinery repeats because our Mobius code is managed. So when someone will call it, it will be JITed by the .NET Core and now execute as a native code. So we have this additional level of indirection, which is mostly painful when the JITed code pretty often calls runtime, Mobius runtime. But it is not so often, in fact, because when your code is being executed, we are mostly calling the runtime for allocations and sometimes for another features, but it is not so often that every method, for example, calls the runtime. So the overhead, for sure, there will be some overhead, but in the end, it doesn't have to be orders of magnitude slower just because we have two runtimes. So this is a picture that in general describes the idea and tries to explain that it is not totally stupid. I hope that you understand it a little more, why I found it interesting, and that makes sense to implement it in the at the first place. Okay, so continuing. And obviously, if you have any questions, just do not hesitate to ask, because this project is all crazy, so questions also may be crazy. Now, so when we have those pieces all together, the question is how the runtime of .NET Core runtime should cooperate with Mobius. So, for example, I could write Mobius that is reusing some parts of the .NET Core. For example, I would be tempted to reuse GC, or at least parts of the GC. Or maybe I could reuse the whole type system, because it is pretty boring to rewrite type system from scratch, so maybe I could reuse it. And yes, probably I could, at least some parts of it, but I was so tempted to write everything from scratch that I didn't do that. So I just literally created new solution, new file, new project, console application, and started to write .NET Runtime from scratch. And obviously, there are some design decisions how to structure your runtime, because we have a lot of pieces that are cooperating together. And I hope I will find it very interesting, and I will learn a lot about all those pieces cooperating each with the other, because we have some blocks. For example, we have host, which will be just something that starts the runtime and executes the application. Then we have the core, the heart of the runtime, and then two super interesting pieces that should be used as plugins, because we want to drive experiments. So I don't want to hard code GC. Moreover, I don't want to hard code JIT. So people will be able to write their own JIT and just plug in into the runtime. And this is a huge challenge, obviously, because there is a lot of let's say, implementation driver contracts between the JIT, the GC, the runtime. So the whole thinking about how the interfaces should be defined, but between all those pieces, is very interesting. And this is one of the reasons why I'll still not open sourced it, because I want to think it the best I can, and then only then open source it. So some design decisions also when created a new solution, when creating a new runtime, for example, whether I should use async or not, or how the JIT should be implemented. And then some boring stuff, and we will return to these design decisions soon. Then some boring stuff. The most boring part when writing your own runtime is to implement type system and the handling of metadata. It is a pretty big part of the ECMA. It is pretty boring because you just need to implement that, okay, this type of method has this type of signatures and this is optional, this is not optional, this is a field, this is a property, and so on and so on. So it is pretty boring, but unfortunately I decided to do that. I'm learning a little bit at least doing that. Then the GC, which obviously is my beloved topic, so I will need to implement GC, and it will be nice that it will be totally written in C sharp, so it could be used for pretty nice experiments even outside of the Mobius environment, and a lot of decisions here, but we will see. I didn't touch GC yet because I'm still on the part of the core of the runtime. Very interesting topic is the object memory layout. This is something not so maybe immediately uh, clear that you need to implement somehow the object memory layout, because the ECMA standard doesn't imply any specific layout. .NET Core has some layout. For example, there is a header, there is a method table of the type, and then there are fields of the type. Mono has something similar, but still there may be some differences. And what I would really have in Mobius is to have an abstraction over the memory layout. So people will be able to create their own memory layouts. We will somehow cooperate with JIT and GC to drive experiments again, to create your own memory layouts and see how they are working, whether they are good for specific purposes or not. So another abstraction that we will need to define to make it all working nicely. Okay, so design fundamentals. First question, whether it should be async or not async. Decision was pretty easy for me. It is not async at all because the runtime is not IO bound. It is mostly CPU bound, so we are just given an IL to interpret and to create a native code from it. So there is no so much IO. So I didn't find any benefits from async, but async obviously async paths provide some disadvantages. For example, I cannot use spans inside, and I cannot use some nice ref structs inside, and so on and so on. So async gives some disadvantages for me at this point, so I decided not to use async at all. Another thing is this flexible object memory layout, and I'm investigating it currently because it is just super heart of the whole runtime, how the object memory layout looks. And I'm looking around to be inspired by maybe another projects. So for example, I found the Truffle. Truffle is a language implementation framework written in Java. So you can define your own languages in Java, and it is also putting a lot of attention to defining object layout because of these new languages that you can create inside. So I'm currently investigating this. This is super interesting on its own. By the way, Mobius could generate tons of master thesis documents, let's say, because it contains a lot of very nice researches inside. Okay, JIT. JIT is the super heart of the runtime because it is the one which is responsible of taking your IL code of the method and then produce something that will be executed. So the very first approach when implementing the runtime, and when you have this IL to execute, in fact, is to use interpreter. Interpreter is in fact not a JIT at all, because it is just taking an instruction from memory one by one and interpret it. In the end, we have something like here as a pseudocode. You have a stream of instructions. You see that, okay, this is an instruction responsible for, let's say, adding. Then I'm calling a method that is adding two numbers from the stack, for example. So interpreter will be a huge loop and with a huge switch inside, which is just interpreting instruction by instruction to execute your program. And this is pretty nice. It has this advantage that it is super easy to implement. You have a set of instructions to interpret. You are writing a method for each instruction, and that's all. And another benefit is that does not require an executable memory region, because you are just taking an instruction from memory and looking what this instruction is and then interpret this instruction. So you don't need anything to write to. And that's benefit, because some environments, for example, limits us to not having executable memory regions that we can write to. But there are some disadvantages. First of all, it is super slow, because it is just instruction by instruction, switch, loop. CPU cannot introduce here any optimizations. The branch predictor is just screaming, because every time there is another instruction in this huge switch. And also here there are no optimizations possible. We are just interpreting instruction by instruction. And by the way, for me, it was not super tempting, because it does not provide any way of learning how to write a real JIT. This is something that we can write, but it is obvious and straightforward, so not so fun. Mono is something that has interpreter mode, and that's why Blazor is using Mono, because currently WebAssembly, which is underneath used by Blazor, does not provide the possibility to write to an executable memory region. So we need this interpreted mode for Blazor currently. .NET Core also has interpreter mode inside, but it is just for experimental purposes. You need to recompile .NET Core with it being enabled. And .NET Anywhere also is using something similar, and that's why it was the very first runtime used for a Blazor experiments. Okay, so I said I will not write interpreter because it is boring. So let's write real JIT, something more similar to real JIT. So we have the advantages of the real JIT, like it might be super optimizing. It is just the sky is the limit how you can optimize code generated by the JIT. What .NET is currently doing, I mean Microsoft, is providing very nice optimizations that are incorporated into the JIT. So the runtime is becoming more and more performant, just because the JIT inside is able to do more sophisticated optimizations. And obviously, writing real JIT allows us to learn how to write a JIT, so it is very tempting. Disadvantages. Obviously, sky is the limit in terms of features, so it might be super hard to implement. We can start from somewhere, but there is no limit where we will end. It is just an endless field of possibilities. And also it requires an executable memory region, which may be a problem, but for me it was not, because I assumed I will be writing it for Windows and Linux, and then there is no this limitation. I can create an executable memory region and write data to there, so no problem for that. This is how every .NET runtime is in fact running. But there is something in the middle. It is called, and it is based on so-called threaded code. This is a technique, and please do not be misled by the multi-threaded concept of threads. Here, threading is from the different meaning, means waving, interleaving, and threading simply. So threaded code is a programming technique where the code has form of subsequent calls to subroutines. So when we are producing JIT, which is working as a threading code, we in fact is producing threading code, JIT emits a code that will just consist of a long subroutine calls. Every IL instruction will have corresponding subroutine to be called. And why it is nice? First of all, it is pretty simple to implement. For example, just a kind of pseudocode from the IL is stacked base. So when we are adding two numbers in C#, in the end it is called and it is translated to the IL, which looks like that. push one number to this evaluation stack, push another number on the evaluation stack, and then call an instruction that will take those two numbers, add them, and put the result on the evaluation stack. So this is how I can produce threaded code from it. I can create an subroutine for every type of instruction, and my code of a method will just be a huge list of calls to a subsequent instructions, subsequent subroutines executing my code. So maybe it doesn't look super sophisticated, but it sounds like a perfect middle ground for such a crazy project as Mobius, because it has tolerable difficulty. It is good for a start. It is easy to grasp how to implement it. It looks like interpreter, but in the end, it is producing some real code. So there is no phase of this interpretation afterwards. We are just producing some native code. It contains of a lot of calls, I agree, but calls are extremely optimized nowadays in CPUs, so it will be not super slow. And it is sounds like a pretty nice approach how we can write something working, which is not so trivial as interpreter. Okay, so those are the high-level concepts, let's say, how we can write it. A few slides about the, let's say, more low-level stuff. So the metadata, we need to interpret the metadata because we have an assembly with our code, and we need to interpret what's inside to read and to understand what's inside. For that, I'm using a pretty nice, great, in fact, library pnet, which is a parser for Windows portable executable files. So I can interpret metadata from there because it also supports a .NET based metadata inside the file. So it is just a few lines of code. I'm just opening a file, then I'm looking inside this metadata defined inside, and after a few lines of code, I have a stream of bytes which are just those that define IL of the entry method. So the main method in case of C#. So pretty few lines of code to get the IL to be interpreted now or executed. So we need JIT because obviously we have IL, but we need to JIT something. So we need to JIT this threaded code. First thing is to get an executable memory region inside which I will be putting our instruction to execute. So I'm creating executable region which is also I am able to write to. And now I have a region of memory that I will be able to write. And then I need only to implement this trivial method, which is here have an argument of the method body. I have a span of byte, which is just a stream of bytes describing IL of the method. And then I just need to implement JIT. I just need to implement the code that will be JITting, producing the instructions representing this IL. And in the end, I will need to call this method that has been JITted. And that's all. So first of all, how I can dynamically create, call a code that has been dynamically created, because my JIT will emit some native code, and then I want to call it from C#, because Mobius is C#, obviously. So there are two instructions, a call instruction that allows us to call a method under a given address. This is an IL instruction. And there is also a instruction called LDFTN, which is instruction taking an address of a given method. So we can combine them and call in from the IL code method under a given address. For example, just to show you an example how those functions, how those instructions are operating, we have here method and taking an address of it, and then I'm calling this with given signature because I have an address of this particular method on the stack. And by the way, this is what function pointers are adding in C#9. It is just exposing those two instructions to the level of C#. So now from C#9, you will have this strange type of delegate, which is just a function to a pointer, and then you will be able to call it, which will emit call instruction inside. And okay, this sounds nice, but all this requires compile time delegates. I don't know what will be those delegates because this is just JIT compiling the code that comes from the application. I have completely no idea what will be arguments and result of the method that I'm JITting. So I'm doing here some magic, and this is one of the first pieces that is pretty low level. That I'm creating a dynamic method and emitting IL code that will call the method under a given address. I will not bother you with details here. All this will be available as a recording. Slides also will be available. So if you are interested, you can follow in details. But this is the magic code that is taking an address of a method and calling it with the help of Kali. Again, as you see, the signature of the method I'm calling here is hard-coded. It is a delegate here expected to take one integer as an argument and one integer as a result. So this is obviously not yet good for my purposes. I need to rewrite it. I need to write something that will generate me dynamic signature of delegate. And this is even more scary code because this is the code to create a delegate with a given return type and parameter types. Again, some magic to create in flight to create a type representing the needed delegate. Even more scary code. But in the end, we have all pieces in place. So we have a way of creating a code. Let's say that I implemented it, and then I have a way of calling it. This is not all, obviously, because we will not JIT everything in advance, everything at all. We need to compile in a lazy way. If only someone will call a method, only then I will JIT this method. So I'm not JITting everything I met when I'm loading an assembly, but instead I'm putting something which is called JIT stub as an entry point for every method that I see as defined in an assembly. And this JIT stub will be responsible for taking IL, interpreting it, I mean emitting the JITed code, and then substitute this method address to this native one. And here the dragons. Like, this is the most interesting part, how to combine all those pieces together to call dynamically, to create dynamic stub that will call the method that will JIT itself. So for example, here I have a method which is the heart of our JIT. It is a JIT method, which is used to be called by the JIT stub. Again, I will not bother you with super details because it is not the purpose here to understand everything, but just to show you how all those pieces are working together. And then we have JIT method, which will be called. And with the magic of GC handles, I'm just getting from this pointer the IL body. And now I have all pieces in place to interpret it, to emit the code for it. For emitting, I'm using another library. It is called ICED. I hope it is spelled like that. It is a super nice high-performance instruction decoder and assembler. So with the help of it, you can generate assembly from the C# under a given address. So I'm creating some memory writer under the given address and then assembling the instructions that I provided here. And this is just writing an assembly because Mobius needs to emit assembly in the end. So I'm just generating assembly in that way. This is a super simple method that is just returning super simple function, in fact, that is creating a stack frame, returning 44 as a result, and deleting the stack frame, just as a hard-coded example of code being emitted by the JIT. Obviously, this one needs to be now in exchanged with the real logic of the real JIT, generating threaded code. And also callbacks. So for example, when my method that I'm JITting requires to call allocator, I need to call the allocator. So I need to use the call method to some pointer that is representing a callback to the runtime itself. And I can create it because in fact, .NET Core provides huge, nicely working, powerful features for that. So when I have a pointer to a method which is taken with this magical method, it creates some super nicely working stub for a given method. And this is, the name is quite meaningful, get function pointer for delegate. And having this pointer, I can safely call it with from within the JIT code, and it will just work. It will be calling this particular method uh, just as a regular method. So out of a sudden, the native code JITed by Mobius will return to Mobius code, and we will be inside our allocate method. Pretty nice stuff. And it will even pass this pointer. So as we will see here, there is no this pointer passed, but it will work, believe me. We're not going into the details. And then we have all the details. We just need to implement the rest of it, the rest of the JIT and the rest of the runtime. So slowly summing up, because the time is ticking, when it will be something that you will be able to play with. So first of all, amount of code that is needed to write your own runtime is infinite, and I don't expect to finish it during my life. Like, it is not possible that single person will write everything implemented as a runtime. But I can write some vertical proof of concept that is just providing most crucial parts of the runtime that will be able to execute super simple application like Hello World. And I'm not putting attention on GC, and also no threading support, at least for now, because it will take some time. I plan to create it as an open source project. It's all prepared for that. So maybe some people will contribute. So it will be on GitHub at some point in time soon. I cannot say when, because absolutely I have no idea. Like, probably you see already that it is totally crazy project, written as a pet project in free time, which unfortunately I don't have a lot. So it will take some time. Maybe I will just decide to open source the current status, and we will see. So why you will be interested in that? Maybe because maybe you have ever wondered how .NET Runtime works, and while digging into the tens, hundreds, thousands of lines of the real .NET Core runtime is really hard, digging into the Mobius runtime code will be not so hard. So it will be pretty nice way of in the understanding .NET runtime, because it will be written in C# and will be not so huge. On the other hand, also, if you have ever dreamed of contributing to .NET runtime, again, contributing to the full runtime is just scary. So contributing to so crazy fun project as Mobius will, I hope, drive a little more experiments. Imagine implementing, I don't know, exceptions, handling specific case of generics or anything else. Everything's up to you. So there is one article on my blog which is explaining the same things, maybe with some more details. And this particular project is still a closed source, but it will be open sourced, as I said, so soon. I'm not sure when. So from my side, that's all. It's crazy thing, as you see. So I hope you find it interesting, at least a little bit. And thank you for listening. Any questions then?